Okay, greetings. So we intend to introduce the Wigner-Eckart theorem. We will be stating it and also proving it, but before that we are sort of laying the foundation for the Wigner-Eckart theorem, which as I mentioned is an extremely important theorem in quantum mechanics, and the foundation requires a very strong background in angular momentum algebra. So we do various things with the angular momentum operators and the irreducible tensor operators. So one of the questions that I am going to discuss today is that if you have a certain vector, what is the condition under which it becomes a vector operator? Is it automatic or is there more to it? Okay. So there are certain considerations which I will be discussing about this, and these are some of the things that we need to equip ourselves to deal with the Wigner-Eckart theorem. These are some of the questions that I want to discuss in today's class, but before I do that I will illustrate how the recursion relations are used, so that you go from one coefficient to another one. And let us take this example over here. We have already discussed this. So what you do is begin with a recursion relation. Okay, we have already established the recursion relation. There are two of them. Let us take this and let us take a special case with m1 equal to j1 and m equal to j minus 1. M can take all values from minus j to plus j in steps of 1. So one of the values is j minus 1. Now corresponding to this choice, in this coefficient here, this quantum number m plus 1 must be equal to the sum of these two, otherwise the Clebsch-Gordan coefficient is 0. So m2 in this case must be the difference between this m plus 1 and m1. So it is m plus 1 minus m1, and since we have chosen m to be j minus 1, it is j minus 1 plus 1 and then you subtract j1. So this is j minus j1. So that is what you get for m2. Okay. Now rest of it is very straightforward, because you just substitute all of these quantum numbers by the specific values for this choice. So wherever you have m, you have j minus 1. So this is a minus m, so you have minus j plus 1 over here. Okay. Here you have m, so it is replaced by j minus 1. Wherever you have m2, like here m2 we found m2 is j minus j1, so m2 takes the value j minus j1 over here. So in this step all I have done is to use the recursion relations and only substituted the quantum numbers appropriately. Okay. Now let us have a look at this further, because we know that some of these terms will get simplified. For example, you already see that the first factor under the square root here is j minus j plus 1. So this is just 1 multiplying the remaining factor, right, and the remaining factor is minus 1 plus 1 cancel each other, and then you have j plus j. So this whole thing will simplify to just square root of 2j. Okay. So let us do that. So this is the same expression which I have brought to the top of this slide, and now I get square root of 2j coming from this term, and likewise I simplify the remaining terms. Okay. This is just mere substitution, nothing very big about it. Now once you do that, you see that the recursion relations are giving you a relationship between three coefficients, 1, 2 and 3, and quite obviously if you write this for this term, okay, it will involve the difference between this term and this term, and that difference is what will let the coefficient go either positive or negative. So there is nothing very strange about a coefficient going negative. It is just the difference between those terms. So, there is nothing very strange about it. So, let me call this as equation A. Okay. Now, let us take the other recursion relation. Now, I am just demonstrating how you play with these terms. You take the other recursion relation, which also we have proved, and in this you set m1 equal to j1 and m equal to j, but in this recursion, in this coefficient, you must have this m minus 1 must be equal to m1 plus m2. So, m2 must be m minus 1 minus m1, but m minus 1 will be j minus 1 because we have chosen m to be equal to j, and then you subtract m1 from it, and m1 has been set to j1. So, m2 now becomes j minus j1 minus 1. Now, you do the same thing again, just go ahead and substitute these terms in the recursion relation. Okay. So, here you get j plus m, so that will become j plus j, and here you have j1 minus m1, but m1 has been chosen equal to j1. So, you get j1 minus j1, that will give you a 0. So, this term would vanish and you will get some simplifications of this kind. Okay. So, this is just a matter of doing this carefully, and I will let you work out the details for yourself. I will only illustrate the technique just so that you know how this algebra is done. So, now you simplify this term, and this j1 minus j1, this first term vanishes, and now you have a relationship between the remaining two coefficients, which is a much simpler relationship, and I will call this as equation B. So, now you have got two results, one that we got from the first recursion relation and the second that we got from the second recursion relation, and these are the two relations that I have called respectively as equations A and equation B. Now, notice that this term over here in equation A is exactly the same as what you have over here in equation B, and you can therefore borrow this result from equation 1 from equation A and plug it over here, or vice versa, either way, right, because these two terms which are enclosed in this blue loop, they are exactly the same. So, once you do that, you have this left hand side, then you have the square root factor which is here, and then this term is replaced by the right hand side of this divided by the square root of 2j which comes over here. Okay. So, this is very straightforward substitution. Now that you have this result, and I write it for this coefficient. So, this square root of 2j I again move to the right hand side. So, this root 2j and this root 2j give me a 2j over here, and now this is the relationship that you get, right, and now you can simplify this for specific values of j1 and j2. So, this is the coefficient that you get in, and you have the same term over here. So, you can actually combine these terms and get the residual relationship which will come out of it. So, you have the same term coming in over here, j1 comma j minus j1 minus 1 is the same over here, and this is j comma j minus 1 which is the same thing over here. So, when you transpose and rearrange these terms, simplify this, and then take specific values, let us put j1 equal to half, j2 equal to half, and j equal to 1, okay, and just substitute these numbers, okay, put the specific quantum numbers in that relationship, and you can get a much simplified relationship. And then this is just arithmetic, this is half minus 1 plus half plus 1. So, minus 1 and plus 1 will cancel, half into half will give you 1. So, you have got 1 multiplying the remaining factors. So, you can do this arithmetic in a very simple manner, but you have to do it carefully, and once you do that, what you find is that these two Clebsch-Gordan coefficients, which is half minus half 1 0, must be equal to minus half, half, 1, 0. That is the result that you get. So, you get some handle on the relationship between the Clebsch-Gordan coefficients by using this. Now, let us extend this further. Let us use this result that we have just got in equation A. Now, when you plug it in and substitute all the numbers, you find that this coefficient turns out to be 1 over root 2. Okay. So, this is how you get specific values, and then of course, you also have the orthogonality relationships, and by making these orthogonality relationships you can get this particular block that we were interested in. Okay. So, using the orthogonality relations and the recursion relations, you can easily get the rest of the terms. So, this is just a demonstration of the technique, and I will let you work out the details. You can get some of the other coefficients just to get some practice. Now, you can also see the same result coming from this equation B. If you handle this equation B in which you had this relationship, you can put j equal to 1, j1 equal to half, and j2 also equal to half, and just plug in the actual values of these quantum numbers and simplify these terms, and you find that this coefficient, which we know has got a value equal to plus 1, right. It has to be, because that is the only one which can generate the state 1 1, okay. That is the only one. So, you immediately get this coefficient to be 1 over root 2. So, there are so many different ways, different routes to get a certain result, and essentially what you are doing is to play with the recursion relations, use the orthogonality relationships, and you will be able to get all the Clebsch-Gordan coefficients just from the seed value, which is this, which is m1 taking its maximum value, m2 taking its maximum value, j taking its maximum value, and m taking its maximum value. That coefficient must be unity. So, that is the seed coefficient, and from this you can get everything else by using these recursion relations. So, now I really take up the question that I really wanted to take up for today's discussion, as to when is a vector A a vector operator, okay, and we know what vectors are, we know what vector operators are, okay, and we need to address this question. And for a vector A to be treated as a vector operator, it must subscribe to the properties for the vector operators, okay. It is not enough that it satisfies just the vector algebra, but it has to satisfy the algebra of the vector operators, and the vector operators we know they transform under rotations according to this rule, okay. So, we have discussed this rule, and we have seen that the Wigner D matrix elements appear in these transformations. So, this is the transformation of a irreducible tensor operator of rank k. You are taking the qth component, and this is the defining relationship. So, this will be our guideline. This is the basic definition of the irreducible tensor operator, and this is completely equivalent to these commutation relations. So, you can define the irreducible tensor operator family by this relation at the top, or equivalently by these commutation relations, the commutation with the generators of angular momentum. So, it is not surprising that this should be involved, because when you deal with vectors you always see how their components transform under the rotation of a coordinate axis, right. The generator for rotations is the angular momentum, which is why the angular momentum operators get involved in the commutation relations which define the tensor operators of appropriate ranks. So, let us take a vector operator, and these are the spherical components. This is an irreducible tensor operator of rank 1, and you can also express the Cartesian components as you always do, okay, and then you have these relationships between the Cartesian components on the spherical components. So, there are these transformations which tell you how these tensor operators are related to the Cartesian components. They both define essentially the same vector operator. So, it is just a matter of expressing them either in Cartesian components or in spherical components. It is much nicer to express them in spherical terms, because that is how the algebra of angular momentum is developed. And to study the fundamental criterion of when a vector A is a vector operator, one must study this response to the rotation. So, let us find an equivalent criterion for this. So, this is the response of a component to rotations, and the corresponding equivalence with Cartesian components is given over here, that if this relation holds, then the commutation of Ai with Gi would vanish when both are the same components. If you take different components Ax with Jy, then this is Ax Jy minus Jy Ax, then this must be I cross Az. Okay, this is very similar to the angular momentum commutation relation. So, the angular momentum itself is an angular momentum vector operator. So, this is natural that you should expect that relation to appear. Likewise, its commutation with the third component Jz will be minus I cross Ay. You can write this as Jz Ax and then it would be plus, but this is Ax comma Jz. So, this is minus I cross Ay, and then you have similar relationships for Ay with the other two components and also for Az with the other two components. So, they are completely, you just change the indices x to y, y to z and z to x, you will get the remaining relationships. So, you get the corresponding relationships by simply shifting the subscripts x to y and y to z and z to x by cyclically rotating them, and you get these two equivalent criterion. One is what is denoted in this inset box, which is the response to rotation. The second is in terms of commutation with respect to the angular momentum generators. Now, let us take some examples. The position vector, the momentum vector and the angular momentum vector. Okay, I take these examples and we ask the question, are these vector operators? Okay, we know they are vectors because we know how their components transform, and we ask if they are vector operators, and what you will do is to subject these operators to the fundamental criterion that we have defined, and if that criterion is fulfilled either in terms of this relationship or equivalently in terms of the set of commutation relations which we wrote down on the previous slide. So, either this relationship or this, and these two are completely equivalent to each other, we have seen that earlier. By subjecting these to the criteria that we have chosen to define vector operators, we can ensure that these are vector operators, but mind you, this certainly depends on how angular momentum J itself is defined, because it appears explicitly in this commutation relation. So, if you have not defined angular momentum appropriately, okay, this will not work, and in a few minutes you will see an example where it will become quite obvious to you as to what is meant by defining the angular momentum appropriately. Okay, but at this point you recognize that it definitely has to be defined appropriately because it is appearing explicitly in the commutation relations. So, this particular feature, as I mentioned over here, it actually determines how the angular momentum J must be defined for a dynamical system. What exactly is the definition of angular momentum of a dynamical system? So, that is actually determined by this consideration, and you will see why this is so important. So, let us refer to this criterion over here, and it is important to remember that this criterion is extremely important, that that would determine how the angular momentum is appropriately defined. If this does not hold for the definition of angular momentum that you have chosen, then it would mean either that A is not a vector operator, or else it could mean that angular momentum has not been defined appropriately. Okay, that is the consequence. Okay. Now, this is the necessary and sufficient condition, that if this criterion breaks down, then it would either mean that this vector A is not a vector operator, or else angular momentum has not been appropriately defined. So, let us take an example here, that these operators that I took for the first consideration, the position, momentum, angular momentum, and we ask these questions that do they satisfy these criteria, and this is a matter of working out the algebra. You can discover for yourself that yes, they are vector operators. What about spin? Is it a vector operator? Okay. Now, here comes the nice answer, that it is a vector operator, but only if angular momentum is defined. If the system already has an orbital angular momentum, then the net angular momentum must be defined as L plus S, which means that the rotation operator, whenever you subject this component to rotations, you must subject the components AI must include the components of L as well as S. If you do not do that, it would mean that the angular momentum has not been appropriately defined. Okay. So, spin would be an angular momentum operator, but only for a system which if it already has an orbital angular momentum, then the net angular momentum will have to be defined as a sum of the two, and this is where the combination of angular momenta J1 and J2, how you couple J1 with J2 becomes important, because you have got now two sources of angular momentum, one is J1, the other is J2, and you combine them using the Clebsch-Gordan coefficients, right. And the two angular momenta in this case, one is the orbital angular momentum L, the other is the spin angular momentum S. So, the spin wave function must be subjected to rotation simultaneously along with the space wave function. Okay, you cannot do just one and not the other. Now, let us take another example here. How about the electric vector, electric field? We know it is a vector. Now, let us ask the question, is it a vector operator? Now, we know what to do. What we are going to do is to subject it to the same criterion, right. Now, this electric field we definitely know is a vector, there is no doubt about it, we have been using it in vector algebra and vector calculus, and it is external to the dynamical system. Like if you have got an electron or an atomic system which you place in an electric field, so now the electric field is external to the dynamical system that you are really dealing with, which is the atomic system or the electron angular momentum, and if you have not included that in the definition of the angular momentum, it will not be a vector operator. So, what you have to do is to examine these commutation relations. These are the equivalent defining criteria, right. So, these are the equivalent defining criteria, and you must subject the components of the electric field to these commutation relations and ask yourself if they satisfy the same relationships as you used to define what a vector operator is. Now, it turns out that if the electric field is included as an integral part of the dynamical system, so you define your system not to be the atom, but the atom plus the electric field, and then define an angular momentum, you can certainly do that, but it will have an extremely complicated form, and that is rarely done. But otherwise you treat it just as an electric vector, but not quite as a vector operator, because we had two options over there, that if the criterion is satisfied, then you know how to define a vector to be a vector operator, and when the criterion is not satisfied, we know that either it is not a vector operator or angular momentum is not appropriately defined. Okay? So, you can certainly include this in the dynamical system, but then the form of the angular momentum would be extremely complicated, and in many semi classical descriptions it is rarely done. So, electric field will be a vector all right, but not a vector operator. Okay? So, these are some considerations which will be of significance to us. So, these are the set of relations. One is this response of the spherical components to rotations, and the other is the commutation of the Cartesian components with the angular momentum components. Okay? And this is natural to expect, because the angular momentum is the generator of rotation. So, that is what defines how a tensor components, how tensor components of tensor transform under rotation of a coordinate system, right. So, these are equivalent definitions. You can use either one or the other. You can derive this from the first or vice versa. They are completely mathematically equivalent, and we will now work further with the irreducible tensor operators. Okay. So, now we have some general similarities between angular momentum vectors and the irreducible tensor operators. You would have noticed them already. You know that both the angular momentum vectors, which are Jm, these are eigenkets of j square and jz. Okay. What is this? This is an irreducible tensor operator which is defined according to the definition as to how its components transform under rotations. Okay. Now, both of them have very similar response to rotations. Now, this is really interesting, because if you look at this relation, the response to rotation of this component is that you get a sum over all the remaining components, the coefficients being the elements of the Wigner D matrix. Likewise, if you see the response of an angular momentum vector to rotation, you have an exactly identical relation. The first relation over here is for irreducible tensor operators. This relation over here is for vectors. How do angular momentum vectors respond to rotations? Okay? So, these are two different questions, but the answers are very similar. The response of both to rotations is very similar, and they involve the linear superposition of the elements weighted by appropriate Wigner D matrix elements. That is the similarity. So, this is our conclusion, that the irreducible tensor operators and the angular momentum vectors have got similar response to rotations. Now, let us plug in another fact that we have learnt, that angular momentum vectors are coupled using Clebsch-Gordan coefficients. We know that. We have learned how to handle this. may we then ask if it is possible to couple irreducible tensor operators using the Clebsch-Gordon coefficients. Okay. So, we are building on the analogy between the angular momentum vectors and the irreducible tensor operators. We find that both of them have similar response to rotations. We know that one of them can be coupled using the Clebsch-Gordon coefficients. We now ask, can the other be coupled using the Clebsch-Gordon coefficients, right. So, let us raise this question. We take two irreducible tensor operators, one is x and the other is t. X is an operator of rank k1, t is an operator of rank k2. So, this will be a family of 2k plus 1 operators, and this will be a family of 2k2 plus 1 operators, and you take one of these elements q1 and q2 element over here and combine them using the Clebsch-Gordon coefficients. Now, this is exactly what we did when we coupled two angular momenta. Okay. See the comparison, means I have written angular momentum coupling. This is a coupled angular momentum kq, which is a superposition. You can recognize this as the resolution of unity if you like. Okay. This is similar to sum over m1 m2 m1 m2, right, Ket-Bra, but I am now using dummy labels to be q's rather than the m's. So, it is exactly the same relationship, and I now have a construct which has been composed using a prescription. What is the prescription? That you have combined two irreducible tensor operators x and t, like over here you combined two angular momenta, okay, k1 and k2. Okay. Here you combine two angular momenta k1 and k2, you can write it in the long notation, so that will make it explicit, because this kq is a shorthand notation for coupling of k1 k2 leading to k and q. K would go from modulus of k1 minus k2 to k1 plus k2, right, and for each value of k, q would go from minus k to plus k in steps of 1. So, you know what we are talking about. Okay. So, this is an exactly identical relation in which you have constructed a coupled angular momentum states from the factor states using coefficients which are the Clebsch-Gordon coefficients, and you use exactly the same Clebsch-Gordon coefficients, namely q1 q2 kq, which are precisely the ones which are appearing here. Okay. This is q1 q2 kq Clebsch-Gordon coefficient in the short notation, which is this, right. It is exactly the same coefficient, and we are now going to ask that if the coupling of k1 and k2 gives you a new angular momentum k, then likewise would coupling of x and t using the same prescription, which is using the same law of combination, the law being combine them using the Clebsch-Gordon coefficients. So, using the same law, the construct that you get on the right hand side, for which you generate a symbol TKQ, is this then an irreducible tensor operator? That is the question. Okay. And we know how to answer it, because whether or not it is an irreducible tensor operator is determined by whether or not it satisfies the defining relationship for an irreducible tensor operator, and we know what it is. Okay. So, what we are going to do is to take this construct, which I have written in the long notation over here just for clarity, but you know the writing k1 and k2 is not important. They are specifically in this context the ranks of these two tensors over here. You know, in the context of the angular momentum coupling, those were the two angular momenta j1 and j2 that we were talking about, and what we do is to state this theorem that if x and t are two irreducible tensor operators, and if they are combined using the Clebsch-Gordon coefficient, which is the same law that you used to combine angular momentum states, right, then the result that you get is also an irreducible tensor operator of rank k, such that k belongs to this range from a certain minimum value to a certain maximum value, and you notice that you once again see the triangle law popping up, and then for each value of k, the q component, which is the member index in that family of irreducible tensor operators, would go from minus k to plus k. So, this is the theorem that one can prove, and all you have to do is to subject it to this criterion, because this is our definition of an irreducible tensor operator. Okay? Now, this is your homework, that you subject this operator to this criterion, and if the response to rotation turns out to be given by an expression of this kind, then you can conclude that it is in fact an irreducible tensor operator. Okay, so that would prove the theorem. I am not going to prove it over here in this class, but you have to manipulate these terms and see it for yourself. So, subject this construct to this criterion. Actually, you can see that the proof is really not very difficult. You can subject it to the equivalent criteria of the commutation relations as well, do one or the other, and now we ask another question. We had combined an angular momentum vector with another angular momentum, then we combined two irreducible tensor operators using the same law. Okay. Now, we ask, if you take one of these to be an operator and the other to be a vector, and construct a new creature which is some sort of a hybrid creature, right, because it is coming from the combination of an irreducible tensor operator and an angular momentum state. Okay. But this is an operator, so this operator operating on a vector, you know, will give you another vector. So, the right hand side is a superposition of vectors, so you know that it will turn out to be a net vector. Okay. And we ask if this net vector will be an angular momentum vector, right, and since this has been composed from a tensor operator and an angular momentum vector, I have denoted it this time by a beautiful bracket. Once we find that it is in fact an angular momentum state, we could use the same notation, use an angular bracket or a circular bracket or a beautiful bracket, it does not matter. Okay. But just to keep track of what we are really doing, I have used different notations, and they are, I think, quite useful, because when you look at angular momentum coefficients, you, and especially when you put in numbers q1 equal to half, q2 equal to half, k equal to 1, q equal to 0, then it is useful to keep track of which is the side which corresponds to the coupled state and which is the side which corresponds to the uncoupled state. So, that is part of the reason I like this notation, in which I use angular bracket on one side and a circular bracket on one side. But now we have constructed, using the same prescription, a completely new kind of vector, in which you are superposing the result of an operation by an irreducible tensor operator x on this angular momentum vector. Okay. So, this operator operating on a vector will give you a new vector, then you carry out this double sum and have each term weighted by a Clebsch-Gordon coefficient. So, this is exactly the same kind of sum as we used when we composed two angular momenta J1 and J2, right. So, our question now is, what kind of a vector is this? And notice that this relationship is exactly identical to the composition of two angular momentum vectors using Clebsch-Gordon coefficient. So, it is exactly an identical relationship, and the question is this beautiful bracket, is it an angular momentum vector? Okay, that is the question that we ask, and to answer this we must examine how it transforms under rotations. Okay. So, you must subject this to rotations, subject it to the defining criterion, find out how the response is. Okay, we will discuss it in the next class. We will see that you can subject it to the defining criterion and it turns out that it is also an angular momentum vector, and that is a very nice feature, because what you find is that what you have composed over here is an angular momentum vector which comes from the result of an operator operating on a vector, and the left hand side is an angular momentum vector. Now just ask yourself, what would happen if you take a projection of this vector on an adjoint vector? If you take a projection, so this is now a ket, you construct a scalar which is a bracket, okay, that is how you get the projection of a ket, right. So, you construct a bracket, a scalar, and that is what you get on the left hand side. On the right hand side you are going to take the projection of this entire right hand side, you are going to take the projection of this entire right hand side on the same adjoint vector. This will factor out as a multiplier coefficient and you will get essentially the matrix element of an operator which is this x into angular momentum states. Now this is the quantity of interest in spectroscopy, okay, because in physics you are always interested in doing quantum mechanics so that at some point you can relate it to observations. And what are the observations? What kind of observables do you really have? You have got the probability densities, for example, the psi star psi, right, or you can have the transition probability amplitudes. What is the probability amplitude that an operator which is going to represent a physical interaction, that you have got a physical interaction, and is this physical interaction going to induce a transition from a certain initial state on the right to a certain final state on the left, okay. So this matrix element will actually give you a measure of the probability amplitude, its modulus square will give you the probability, and then when you put the right numbers this will give you a measure of the intensity of the transition from an initial state to a final state. That is what you are doing in a spectrum. When you look at a spectrum, right, you see various lines with various intensities, and these intensities are proportional to the transition probabilities which are the modulus square of the transition matrix element, which is a creature of this kind, and the Wigner-Eckart theorem addresses this matrix element. What the Wigner-Eckart theorem does, and that is our topic for discussion tomorrow, that it will factor this matrix element into two parts, a physical part and a geometrical part, okay. So that will be our topic for discussion in the next class. If there are any questions today, I will be happy to take questions.
Sir, electric vector, you are saying about the vector operator.
Yeah.
Where is the application of it?
Sorry?
Where is the application point of view? Where we
Yeah, so the question is, whenever you have an interaction of the electric vector, when you place an atom in an electric field for example, then the electric field vector will not be treated as a part of the angular momentum of the dynamical system. So you have to define it correctly. It will generate a perturbation, okay, but it will not be a part of the angular momentum, and therefore it will not be an operator.
can be an internal.
Yeah, you can do it, but that is not particularly advantageous in this case, because you can generate an angular momentum which will include that, and have an angular momentum which has got an extremely complicated mathematical form, and if it is not of much interest, there is no need to do that, but in principle one can do that. And if you are keen that it should be defined as an operator, then you will have to include it into the definition of the angular momentum. Any other question? Well, thank you very much.